All right, so now we are doing one last example where we're looking for absolute extrema of a function. But in this case, the closed interval method won't work. We're going to have an a and a b here, and the closed interval method is going to fail in both cases. So the function that we're working with is f of x equals 8 over x squared minus 4, and we want to find absolute extrema on both of these intervals right here. So why will it not work to use the closed interval method? Well, for this first one, we are looking at a closed interval, but this function is actually not continuous on that closed interval. If you look at the denominator, x squared minus 4 is equal to 0. If we set it so it's not equal to 0, because that's where our function is not going to be defined. That's the same thing as x plus 2 times x minus 2, not equal to 0, so that x cannot equal plus or minus 2, okay? We know that this function is not defined at either of those values, but the positive 2 is actually in that interval. So I can't use the closed interval method since we don't have continuity here. So what do I do instead? And let me actually make a note of that. Not continuous at x equals 2 specifically, because that's the one that's in this interval. Well, what I could do is, instead of trying to use the closed interval method, I could try and graph this function. Because if I could graph it, I can kind of do a visual check for where these critical values might occur. Now, you can do the graph either using the methods that we talked about in the previous section, which I would encourage you to do. You can also check it on a graphing calculator. One thing I would point out is that where this function is not defined, where x is not equal to plus or minus 2, those are going to give me vertical asymptotes. I'm looking at a rational function, and nothing is going to give me a 0 in my numerator. They only give me zeros in the denominator, so I have vertical asymptotes there. So if I were to graph this function, and I'm not even going to just graph it on that closed interval, I'm going to graph the whole thing, then at -2 and +2, we're going to have vertical asymptotes. In addition to that, because the degree of the numerator, which is actually 0, has a degree of 0, is smaller than the degree of my denominator, we know that as x goes to either infinity or positive or negative infinity, this function is going to shrink to 0, because that denominator is going to get really, really big while my numerator stays at 8. So the function is going to go like towards the x-axis, towards 0, this direction, and then I need to figure out what's going on at these vertical asymptotes here. So again, remember the way you can check that, if I did the limit as x approaches, let's say this +2 right here, from maybe the right of 8 over x squared minus 4. We can do this one kind of by thinking it through. So if x is approaching 2 from the positive side, that means I'm using values that are just slightly larger than 2 when I'm plugging them in for this x here, but getting closer and closer to 2. If they're slightly larger than 2, when I square it, I'm going to get a number that's slightly larger than 4 here, and subtracting 4 from that will still give me a positive number, but one that's very close to 0. So I have a positive number over a really, really small positive number, and that number is going to continue getting smaller, but it will remain positive. Big numerator over a small denominator, both positive, that would give me infinity. This is one of those infinite limits, okay? If I approach 2 from the negative side, I don't know, I put a 1 there, negative side, of 8 over x squared minus 4. Now I'm still approaching 2, but I'm using numbers that are just slightly smaller than 2 when I plug them in here, which means when I square those, I'll get a number that's just slightly smaller than 4. A number that's smaller than 4, minus 4, will be negative, but as this value gets closer and closer to x, it'll be a negative number that's getting really, really close to 0. So again, positive over negative is negative, and because my denominator is getting close to 0, whereas my numerator is not, this is approaching negative infinity. And if you remember what this tells me about my graph, as I approach from the positive direction this way, we're going towards positive infinity. Don't forget that I have this horizontal asymptote here. And as we approach as we approach our horizontal asymptote from the right, we're going to do something like this. It's going to be going downhill. Now, what's happening with the rest of the graph between -2 and +2? Well, within there, I have a y-axis, and I could find my y-intercept by just plugging 0 in for x. So if I found f of 0, for example, what is f of 0? Well, that would be 8 over -4. Plugging a 0 in for x gives me 0 minus 4. So that's 8 over -4, which is -2. That means my y-intercept is 0, -2. So if this is -2 right here, then my function is going to do that, okay? Now, I don't remember if we've talked about this in this class before, but you can use something called symmetry. This function has what's called even symmetry. It's because of the x squared minus 4 and the 8 up here, which basically means that this graph has symmetry about the y-axis. Whatever is going on to the right side of the y-axis, you can reflect it and get something like a mirror image of that on the other side. Now, if you don't know about even and odd symmetry, that's okay. You could do the same kind of analysis that we did here, but with this -2. You know, let x approach -2 from the right and from the left, but you'll get stuff that's going to point you towards this graph right here. Okay. With this graph now, I can take a look at this closed interval from 0 to 5 and see if I should expect to find any absolute extrema at all. So here is 0 right here. 5 would be like way out here. So I can extend that out. Now look, between 0 and 5, I have this vertical asymptote, and as I approach that vertical asymptote from one direction, this goes towards -infinity. That means there is no absolute minimum for this function on that interval because this keeps getting smaller and smaller without ever stopping. There is no lowest point. Similarly, as I approach 2 but from the right, my function is going towards positive infinity. So there is no chance of there being a highest point if this just goes up indefinitely, okay? So for A, there is no absolute extrema on that interval, on 0, 5. We don't get either type, no absolute extrema on that interval, okay? Let's look at this other one, B. I'm gonna go like that to separate. Now we're looking at the interval from -1 to 1. Well, on the interval from -1 to 1, we do have continuity because I'm not hitting either of those asymptotes here. But it's an open interval. It's not a closed interval. So I can't use the closed interval method if we aren't using a closed interval at all, right? So let's think about what happens here. Now I'm looking at this smaller window of my graph. And again, since I've graphed it, I can use that to my advantage. What would the highest and lowest points be? Well, I do see a highest point right here. So there is no point within this window that's higher than that one. I know that it occurs at -2, so that's automatically going to be my absolute maximum. -2. What is the absolute minimum? Well, it's tempting to say that the absolute minimum occurs at either of these points right here. But the problem is that if that were the case, then I'd have to be able to plug a -1 or a +1 into my function to give me those points. But the open interval does not include its endpoints. So -1 and 1 are not available as x values if I'm using that interval. So then what is the lowest point here? Well, the lowest point doesn't actually exist because as I approach this hole, I can keep getting closer and closer to whatever this y value is right here without ever reaching it. So you might think, well, it's got to be the next largest number than whatever that is. But when you talk about the real numbers, there is no next largest number to any real number. Because if you take any two real numbers, like say you're on a number line, and you think, okay, here's the number 2. What's the number that's right next to the number 2? Let's just call it A. I don't know what it is. Well, you can always average these two numbers to find another real number right in between, right there. And that would be closer to 2 than A would. But then if you think, oh, maybe that's the closest number to 2, that's like the next number after 2 in the real number line. But then you can just average those two numbers and get another value that's even closer to 2. So the point is that there's no real number that's right next to any other real number, because you will always be able to find more numbers in between. And that property means that there is no number here that is closest to that whole. The result of that is that there is no absolute minimum. No absolute minimum on this open interval. And so now hopefully you can see why we need a closed interval with continuity in order to have the extreme value theorem. Because for this function, whether I'm looking at a closed interval on which that function is not continuous, or if I'm looking for an open interval, whether or not that function is continuous there, we can end up in a case where we do not get one or both of those absolute extrema, right? None of the absolute extrema happened there. We only got one type here. Okay, so that's it for section 3.4.